Good morning. Happy New Year to all of you. This is our first ERCI webinar in 2026. It's on AI-driven rail infrastructure monitoring. My name is Lutz Hübner from Berlin Partner, one of the 18 ERCI member clusters. First of all, allow me to express my deep distress over the train accidents in Spain that occurred within the last few days. I am sure that I am just speaking on behalf of all the ERCI cluster managers in extending our heartfelt sympathy to all those affected. Thank you. First, I will show you our general agenda. We will have two interesting presentations on AI-driven rail infrastructure monitoring. We will have Q&A sessions after each presentation, and we will present to you some news from the ERCI network. First of all, what is ERCI? It is the leading LiDAR cluster of the railway sector in Europe. We are 18 innovation-driven clusters, and we are operating in 17 European countries. ERCI is now a European rail data cluster established as a Belgian-based association. We are connected with over 3,100 companies, of which the majority are small and medium-sized enterprises. And we have good connections to over 500 universities and research centers and education institutions, incubators, accelerators. It's all about bringing customers, suppliers, and supply chain opportunities together. What we are doing, we are supporting small and medium-sized enterprises. For instance, supporting them in partner matchmaking in research and development activities, discovering new market opportunities, and enhancing the visibility on international level. We are discussing with them innovation topics like cybersecurity, multimodal logistics, green and sustainable mobility due to our task forces. We are establishing networking opportunities like these webinars and workshops, networking events, fairs, and business trips. And our yearly highlight are the annual ERCI Innovation Awards. One example of our task force discussion is on green and sustainable mobility, which will analyze, describe, predict the central role of the rail sector in the transition to our environmentally friendly transport and mobility, and as well its combination with other modes and transport. To get some insights from you, what means sustainability to you, we are kindly ask you to contribute to our quarterly questionnaire. So you will find the link in the chat, and we would be very pleased if you take the time to contribute to this very short questionnaire. These are only 3 questions. Yeah, we can be found for sure in the internet, on LinkedIn, and for sure we have also an email address. You will find it in the chat. And that takes me to introducing the first presentation, but this introduction will be done by my colleague Rico Siegmund from RIMF.
Thank you, Lutz. Hello everybody. Welcome to our webinar. My name is Rico Siegmund from the German-based railway cluster RIMF. I have the honor to introduce our first speaker, Mrs. Julia Richter from SIGNON, Deutschland. Julia studied electrical engineering at Chemnitz University of Technology and earned her doctorate in computer vision and machine learning. At first, she worked in the automotive sector and was responsible for the function and software division. But now she's at SIGNON as a software engineering specialist. and she's leading the innovation project SIGNON Infra AI Technical Equipment and works on innovative solutions for AI-supported registration of railway infrastructure. So, Julia, the floor is yours.
Yes, Rico, thank you for your kind introduction. And yes, good morning, everyone, also from my side. I'm happy to be here, and I'm also happy that you're here. I'm Julia. I'm working at the SIGNON company, and we are a company of the Deutsche Bahn AG and are expert for railway system projects. So our solutions range from consulting to engineering, software, railway power supply systems, right through telecommunication systems. And today I want to present you one of our innovation projects. So let me share my presentation now. Yes, I would like to present you one of our innovation projects, and this project is about automated inventory of railway infrastructure using artificial intelligence. I hope you can see my screen now. Yes, perfect. Yes. Yes, as you might see on the image on the right, we are working on point clouds. But before we come to point clouds, let's first answer the question, why do we need railway infrastructure inventory? I have brought two use cases for you here. The first one is before reconstruction or new construction projects, you need an up-to-date digital planning basis. Yeah, so you want to know where your infrastructure components are installed, which components are installed, and at which position. And therefore, you need inventory first. Another use case is after the construction in terms of construction inspections. Yeah, so after a construction, you want to know, has everything been installed at the correct positions? Has every infrastructure component you planned, has it been installed at the right place in the correct position? Yeah, those are two use cases. And now let's have a look at how infrastructure inventory is performed to date. Yeah, you very often have on-site route inspections. You might, think it's time-consuming, and if it involves track closures, it's also expensive. Yeah, and you have to walk over the track, and it takes very long. Another option you can do is to have measurement campaigns. So you install sensor systems in front of your train, and then you drive along the track and record point clouds, for example. And then step by step, you have to go through the point clouds and check your infrastructure components. You also can imagine this is time consuming as well, very, very tiresome, yeah, when you have to go through all the point clouds, and therefore it's also error prone. Yeah, to summarize, all those manual or semi-automated automated methods are time consuming, expensive, they require expertise, and they are also error prone. And that's why at SIGNON we propose an AI-based analysis of point clouds, and we call this SIGNON Infra AI Technical Equipment, in short, TECI. And this AI analysis embeds in a tool chain that is composed of measurement campaigns, post-processing, the analysis itself, and comparison and update of databases. So in the measurement campaigns, you register your infrastructure using multi-sensor systems, yeah, by installing sensor systems in front of the train, driving along the track you want to record. So here we have LiDAR sensors for point cloud registration, we have GNSS for positioning, and we have cameras mainly for color information. Then this data is post-processed to obtain the sensor system's trajectory, to georeference the data, and also to colorize the point cloud. This data is an input to our AI analysis. So what we do is a point cloud segmentation. So for every point in the point cloud, we assign an object class. Yeah, for example, does this point belong to a catenary pole? the output of the segmentation are then several points belonging to catenary poles, for example. And now if you want to measure an instance of a catenary pole, you first have to do an instantiation. So you also assign the object instance to every catenary pole point, for example. So instance 1, it belongs to catenary pole 1. Instance 2 belongs to catenary pole 2, and so on. And then when you have the points belonging to every instance, you can also perform measurements on the instances. For example, where's the anchor point of the object? In our case, right now, we measure the center point of the object. And then in the last step, you can compare and update your databases if necessary. And yeah, what is the advantage of such an AI-based solution? You can see it here on the image. When you have the task now to record or to make an inventory for all catenary poles or Excel counters, you have to go through all the catenary poles, which are very many, or a lot of them are there in the point cloud. And for Excel counters, for example, they are very small. You have to find them first. And here, the AI can help you by just highlighting and finding those objects automatically. So let's have a brief look at the project plan. So at the beginning of our project, we analyzed requirements and worked on the concept. And then based on the concept, we developed our prototype. So here we started labeling data, trained machines, tested and evaluated those machines. And then we worked on a minimal viable product, on an MVP. So we added more objects there, worked on performance issues, and created an interface for a downstream tool chain. In our application, it was QGIS, which is an open geo tool. For the prototype, we started with 3 different objects. You see here Excel counter, pre-signal sign NE3, and catenary pole. We have chosen Excel counters because they are very challenging objects. Yeah, they are very tiny compared to the surrounding scene. They don't really stand out in terms of color and geometry, so it's really a challenge here. For pre-signal signs, we wanted also to know that we can distinguish between the 3, the 2, and the 1 black stripes, and then catenary poles which represent large objects. Then for the MVP, we added more objects, so track method, balizes, blocking signals, and speed limit signs LF7. Yes, and then we did what everything does when he or she wants to train a machine. We labeled a lot of objects. We annotated those objects, so we cut them out. And then this is the basis for our training. So we trained a 3D segmentation net. And the output then is a point cloud with the aim that every object point is classified as an object class. We also performed a feasibility study, so that involved 3D network selection. Also, we removed irrelevant regions and we split our clouds into smaller tiles to achieve a higher resolution and also to perform the GPU load and enable a faster training and faster inference. So here are first examples of our or results of our prototyping. This is an example for NE3 and catenary pole segmentation. On the left side here, you see the label. On the right side, you see the prediction. And the gray points are background. And here the green points, the dark green points are catenary pole. You see on the right side, it was predicted also very well. And here we have the NE3 with 1 stripe. It was predicted as an NE3 with 2 stripes. Here's a result for Excel counter segmentation, also for catenary pole as well. Yeah, catenary works very well here, and also Excel counters here labeled in blue, yeah, bright blue, are detected and segmented correctly. Of course, we also had some things that have not worked in the prototyping phase. For example, we had rays predicted as Excel counters, or also other signs like here in the bottom that were classified as NE3 because the machine did not know any other signs. Everything was NE3 that looked similar. Yeah, then we had some misclassification in the overhead lines and also false negatives for Excel counters. We worked on that in the MVP phase and improved, and now those are some example results from the MVP. So here you see the segmentation result on the right image. See the catenary pole was segmented, and we have here a track method in blue. And also an LF7 here in magenta. There we have another example here with an Excel counter. I hope you can see it. It's here the object in red, and we have SP dwarf here in yellow. And here's an example for NE3 segmentation, where you can get an impression how this one is segmented. And also balizes and track methods. So here you have in red the balizes, and here again a track method, which are segmented in the point cloud. So let's also have a look at positioning accuracy results. So for correctly detected instances, we calculated the difference between the mean of the labeled object points and the mean of the segmented object points. With that image here, you can see here when we calculate the mean Euclidean distance, we have those results, and when we have the median Euclidean distance, we have those results in centimeters. So we are here in a very good range. Here for catenary poles, we had some outliers, a few. So this is because of when we have such a segmentation, for example, then the red one was the true positive, and the yellow and the green ones were also segmented to be catenary pole points. Blue is background, and here those don't count for the final true positive. Those are false positives. Yeah, but the actual label is the whole catenary pole. Yeah, so the center point of the label, the white one, is here in the middle, and the center point of the classified or segmented true positive is here a little bit far away, and that's why we have here several centimeters difference, and this leads to this comparably high mean Euclidean distance value. But yeah, the majority you see is in the range of 2 centimeters or below. Now let's come to the database update. So what can we do with all the recorded objects? Well, when you have those dark blue objects here in the database, that one and those two, that we can have different cases. The first case is here the green one, that you have a recorded object. It is also present in the database. So it's here in the point cloud, the green one. And if this is the case, you can just confirm, okay, we have detected the object which is already in the database. What can also happen, we can have newly recorded objects. Those are the orange ones. So they are not in the database, but they are up to date in the actual scene, and so you can add them to the database. What can also happen is that here the red objects, that they are in the database but not present on site anymore. Yeah? So there's no object at all. So you can delete the object in the database. Now also let's have a look how it looks in QGIS when you have imported a point cloud there. The advantage is that you can find objects that are not present in the database very easily. Yeah, so in a manual approach, you would not find them. You can't really see the objects here in the point cloud. But the AI enables this and highlights those objects and also outputs the center points of the objects. So I also have another example here for catenary poles and Excel counters. So for Excel counters, again, it's very difficult. Maybe you can guess that those are here. Maybe you can see them in the point cloud, maybe not. But the AI highlights them here in magenta and also highlights a catenary pole here in blue. And so you can easily and automatically find them. I've also brought you a video using QGIS. So here you see the NE3. The red point is the imported object point we calculated with our AI solution. And then when you want to update your database or you want to shift this point to a new measurement position, you can do this manually here in QGIS and then update data point positions. So yeah, to summarize, our AI is like a second pair of highly precise eyes. Yeah, only it never gets tired and delivers results in a fraction of time. Yeah, we have weeks instead of weeks, we only have a few hours or days. We have fewer staff hours. There are no track closures anymore. And the AI closes the gap left by the shortage of specialists. The AI never gets tired, yeah, and whether 1 kilometer or 10,000, the AI analyzes them all. So what are our main next steps? We want to work in further pilot projects, are looking for further projects. Would also like to add more objects depending on the application. Yeah, objects such as light signals, for example. And what it's also sensible and possible is more fine granular object segmentation, depending on the application. For example, when you overhead catenary systems, maybe you want to know whether you have insulators, where is the pole, what is the height of the pole, which kind of pole types do you have. Maybe you want to segment your foundation to measure your foundation or the center point of your foundation, and also catenary wires, droppers, contact cables. Yeah, this is all possible, and we want to work on such projects in the future. Before you come to questions, I would like to show you a short, briefly the results in our point clouds. And also there's a hint from my side. We have a publication in the Eisenbahningenieur. So if you are interested, please look there on the QR code. Okay, so I will end the presentation and switch to another one. Just a moment, please. So here, I hope you can see the new screen now. Yes, if not, just tell me. So here is, okay, perfect, Lutz. Here is a kind of intermediate representation which we used for our prototype evaluations. So here you have already seen this in the presentation, but still I want to show you. You have here the catenary pole. Here you have the NE3 with one stripe. This is a label right now. And here we can switch to the prediction. And then you can see, what you also have seen in the presentation, that we detect the catenary pole and the NE3. So it looks like this. And then I have the example with the Excel counter. So here, this is also the label. Yeah, we have labeled the Excel counters here. And this is the Excel counter, this is the catenary pole. And when we now switch to the prediction, you can see that those were detected, segmented in that way. I also want to show you some point clouds. So this is how it looks like in the real point cloud then. We have here everything which is white or light gray. This is background. And then we have here the green one is the catenary pole. When I rotate it, I hope you see the rotation. You can also see how the catenary pole is segmented from the cable here. Yeah. And here you also see the axle counter and the SP, the Sperrsignal, the blocking signal. Yeah, we also have here some other segmentations, but let's go maybe back to this one. Yeah, this is here, yeah, the prediction. And now when we have a look at the ground truth, yeah, so what we store in user data here is the ground truth. And now you compare it against the prediction. You see that the prediction or the segmentation results are really good. Yes, so now I'm at the end of my presentation. I thank you very much for your attention. Welcome your questions and hand over back to Rico.
Yeah, thank you, Julia. So then we will start the Q&A right now. So first question, can your solution be extended by other objects?
Yes, our solution can be extended by other objects. So what we would have to do is just to add more labels, to add more scenes with objects or with labeled objects. As I said, the light signals, for example. And so yes, we can extend the solution.
Okay, next question. Who can profit from your solution? What are the use cases?
I already have outlined this a little bit in the presentation already. This is, yeah, use cases are when you want to register your infrastructure, for example, before you want to start a construction project, that you know where are your objects so that you can do up-to-date line of sight checks, for example, that you know during the planning phase where you can put new objects and still your line of sight conditions are still valid, that no object occludes the other one. Or also when you, after the construction phase, want to check whether everything was constructed correctly, then you can make a measurement campaign, and based on the point cloud data, you can automatically register the current status of your construction and compare against your plans. Yeah.
Okay, thank you. Next question. Does this technology enable the detection of damage to the track that is currently detected by ultrasonic?
Damage on a track. Can you clarify what kind of damage it is? So my question is because is it physically able, or are we physically able to detect it with point clouds?
Maybe this question come from a participant. So Juan Garcia, please, can you unmute yourself and clarify the question a little bit?
So which kind of damages can be detected with ultrasonic escalation?
Yeah, hello. Thank
Hello,
you for
hi.
letting me participate in. Yeah, the issue is when part of the rail is broken with a very thin line due to a ground union between the rails.
So when there's no union between the rails anymore, and it can be seen in the point cloud, when the sensors are able to kind of register the hole between the rails, I think then it's possible. So when you have a geometric feature which you can detect in the point cloud, and it's not a too small gap in between, then I think it's possible, yes.
And also, for example, the weld joints in the parts of the rail.
Sorry, I didn't get that.
The wheel joint. When you have two parts of a truck and gets together, are welded. That union
I don't
of
have
parts
an
of a
image
truck.
I don't have an image in mind right now. What you mean? Maybe we can keep contact and clarify this in an extra meeting, because I don't really know what you mean exactly right now.
Okay. No issue.
Thank you.
If I find a picture, I will put it in the chat.
Yeah,
Gemeint
perfect.
sind wohl Schweißstöße.
Schweißstöße.
Wenn Schienenstücke
Schweißstöße,
zusammengeschweißt werden.
So damages in the Schweißstöße. I'm not really sure. If the damage is too small and can't be really represented in the point cloud, then it will be difficult to detect such small damages. But if it's damage that results in a geometric feature you can detect in the point cloud, then I think it's possible.
Okay. How big should be the gap in the error on the track to detect that we have a hole in the rail, for example?
This depends on the point cloud resolution. Yeah, so when the resolution of a LiDAR sensor is high enough, then you can detect it. If it's too low and you can't really measure it, yeah, it's I think a question of measurement, then you won't be able to detect it. Yeah.
Okay, depends on the LiDAR precision.
Yeah. Okay. Yeah. Thank you.
Okay, let's move up to the next question. How much recorded data in terms of kilometers was necessary to achieve this level of precision?
The data we have, or the overall data we have, is around about 100 kilometers, but we have not used all the data, only a fraction of that. I would say maybe 40% of the 100 kilometer we used, roundabout, or 40 kilometers roundabout, I would say.
Okay. And next question, which an average cost of 100 kilometers of line of doing this campaign of object detection and database construction?
Okay, so the question is about what are the costs to achieve this kind of result? I can't say right now. Well, I can't answer these questions right now, so I would have to check again what the costs are, because I can't give an exact number right now.
Okay. Is the data collected using drones, or do you use trains equipped with measuring technology?
Yes, the data is collected with collected by using trains equipped with measuring technology. So actually, when we have drone data, I think it's possible to also übertragen, to apply our solution also on drones. Might be that transfer. Thank you. Transfer the solution to drone data. Here it's also a question of resolution. So I think for catenary poles should be working quite well. When we have a look at Excel counters, here again we should check whether the resolution is okay, whether enough points are on the Excel counters, and whether they are still visible in this data. Yeah.
Okay. Have you applied the concept to reinvestments, meaning the replacement of old catenary systems, and may include ground penetrating radar?
I don't get the question.
Okay, then maybe we ask Peter Milander directly if he can clarify this question a little bit.
Yeah, thank you very much for a very good presentation.
Yeah, thank you.
In Sweden right now, there is a big need to invest in the infrastructure, meaning for example, to replace hundreds or thousands of miles, kilometers of catenary systems that are maybe 100 years old. That is a task with a few challenges. Another part of Deutsche Bahn is using a Swedish ground penetrating radar system. I think it's Deutsche Bahn Engineering Systems or something rather.
Mm-hmm.
And they mount the ground penetrating radar on a small vehicle and get an understanding of the geological foundations. However, when it comes to catenary poles that are standing a few meters on the side, that has some challenges. There's also a need to understand and create point clouds of the infrastructure to be able to do a efficient project preparation for the
Yes, so
reinvestment. So there are some parts of the Deutsche Bahn organization that are into this area. And I was wondering whether or not you were actually working with them as well on topics like replacing infrastructure.
as far as I know, we are not included there yet, but I might be wrong. Yes, but with our solution, it would be a very good application or use case, yeah. So to capture the position of the catenary poles, and then also after reconstruction to measure whether they are on the right position. Yeah, this is exactly the use case we are addressing. Yes. Have I answered your question so far?
Thank you. Yes.
Yeah, thank you too for your question.
Okay, then the last question. What processing steps are needed before the data can be used by AI models?
Well, we have colleagues. I'm not the expert in the pre-processing, but we have other colleagues in another department of SIGNON who are working with that. And there we first have to process the raw data to georeference the point cloud so that we are in the DBRF system so that we get the georeferences. Also, we have to colorize the point cloud so the LiDAR sensor itself does not give back the color information. So we have to kind of add this information for every point. And also we have to post-process the data so that we get the trajectory. Actually, those are the main steps I have in mind. There might be others, but my other colleagues from rail are experts or more expert than me.
Okay,
yes.
then.
Thank you.
Thank you, Julia, for the presentation and for answering all the questions. I like to hand over back to Lutz, and he will introduce our second speaker.
Yeah. Thank you, Rico, and to all of you, for sure, please continue to use the chat for your questions for the last presentation and also for the next presentations. And as soon as we have time to clarify the questions, we will do so. So the second presentation is from ApoSys, mainly based in Canada, but also based in Singapore. It's on AI-driven infrastructure monitoring and is introducing the Apollo framework for smarter, safer systems. Our both speakers are Pragya Saxena. She is an AI infrastructure specialist at ApoSys Technologies, where she bridges advanced machine learning with real-world infrastructure applications. She develops AI-driven inspection and monitoring systems and collaborates with railway operators and technology partners to enhance safety, efficiency, and digital transformation across global transport networks. She will be assisted mainly in the Q&A session by Oliver Wang, co-founder and CEO of ApoSys Technologies, leads the company missions to digitalize inspection using AI-powered sensing and automation. With over a decade of experience in transportation technology and systems integration, he has spearheaded multiple deployments across Canada and Europe. I first give the floor to Pragya. Please start your presentation.
Thank you so much. Just give me a second.
And speak a bit louder, please.
Okay, got it. Okay. Can you hear me and see my screen?
Perfect.
Okay, perfect. So, yes, hi everyone. Thank you so much for joining us today. And a special thank you to Lutz and the entire ERCI team for the opportunity to present. So, my name is Pragya. I'm the AI and infrastructure specialist at ApoSys Technologies. And I'm joined today by Oliver, our CEO, who will be supporting the discussion and joining us during the Q&A. So to start, I'll first give a quick introduction to ApoSys and who we are before diving into how we approach digitalizing infrastructure monitoring. So ApoSys is an infrastructure technology company. We're based in Canada, and we've been delivering AI-driven solutions for the railway sector since 2021. Our core focus is the intelligent monitoring of critical physical infrastructure, or CPI for short. We operate across the full stack, from edge sensing and data acquisition in the field to AI-driven analytics and decision support platforms. This allows us to design systems that are not only technically robust, but also operationally practical. So we work closely with multiple academic partners to advance our applied research and collaborate with international industry partners to support real-world deployment. Our internal team and advisors bring over 20 years of real industry experience, and we also work closely with the National Research Council of Canada to support technology development and validation. So when we talk about railway monitoring, we're not referring to individual components in isolation. At ApoSys, our scope spans both track and civil infrastructure, including rails, ballast, bridges, tunnels, and culverts, as well as the environmental and geotechnical risks that influence how these assets behave over time. So a key principle behind our approach is that infrastructure condition is always shaped by its context. Assets degrade not only due to load and usage, but increasingly due to climate change, driving more extreme temperature cycles, higher moisture and precipitation, altered drainage conditions, and changes in surrounding ground behavior. Rather than treating assets as static objects, we focus on understanding infrastructure condition within its environmental and geotechnical setting. This allows us to better interpret current conditions and anticipate how they are likely to evolve. As rail networks become more complex and operationally constrained, the way infrastructure is maintained needs to evolve. Aging assets, increasing climate stress, and growing service demands are placing immense pressure on traditional inspection models. Inspections today are still largely manual and periodic, often limited by workforce availability. Many networks rely on dedicated inspection trains or track recording vehicles, including specialized inspection trains such as Dr. Yellow, which require dedicated track access and operate separately from regular service. This limits operational flexibility and network capacity. As a result, maintenance remains largely reactive, with issues addressed only after defects appear. Predictive maintenance provides a way to move earlier in the life cycle, reducing disruption while making better use of limited resources. So AI is already being introduced in rail infrastructure monitoring to reduce the reliance on manual inspections that I just talked about. Today, it's commonly applied to inspection images and videos, as well as track geometry and condition measurements, helping operators detect defects and flag assets that require review. Where AI performs well is in identifying anomalies at the asset level. However, limitations begin to appear when these models are deployed in isolation. While large volumes of data can now be collected, many systems still struggle to process and integrate this data at scale, especially in near real time. Most AI models are still trained on siloed datasets and lack integration across inspection, asset, and operational data. As a result, decisions remain driven by static rules rather than evolving conditions. AI outcomes are ultimately constrained by how AI is structured and connected, which is why a holistic approach to how AI is built and what's it built on matters just as much as the models themselves. So that's exactly why we designed the ApoSys AI layer stack. It's based on the idea that AI capability is shaped by the layers beneath it. For railways, the stack starts with the physical CPI asset network itself, railways, tunnels, bridges, drainage, and related structures, which form the foundation of everything above. On top of that sits the context, including operating constraints, engineering rules, and technical context. This defines how these assets are actually managed in practice. The data pipeline then brings together inspection data, environmental inputs, asset inventories, and historical incidents in a structured and traceable way. Only with that, the foundation in place does the AI layer become meaningful, supporting risk inference, forecasting, and prioritization, and ultimately enabling applications that operators can trust for planning, decision-making, and reporting. This layered approach is what grounds our AI in engineering reality rather than isolated data signals. So in this stack, ApoSys primarily focuses on the context layer and everything above it. That's where raw asset data is transformed into operational understanding through structured data pipelines, analytics, and decision intelligence. From here, I'll walk through each of these layers and show how we design our solutions using this stack in practice. So the first layer is context. This is the layer where we capture how the railway actually operates, including asset criticality, access limitations, engineering assumptions, and regulatory expectations. At ApoSys, this layer acts as the interface between real-world operational knowledge and the data itself. It translates how engineers and operators think about risk and constraints into something AI systems can interpret, ensuring outputs reflect what can actually be done in practice. The next layer in the stack is the data pipeline. If you recall earlier, I mentioned that while many operators can now collect large volumes of data, not all systems are able to handle or process that data effectively. This is where our data pipeline comes into play. Once we understand the customer's operational and engineering context, we move into the technical context. Data is collected through our onboard hardware unit, which we call the Autonomous Track Monitoring Unit, or ATMU for short, and it is combined with satellite imagery, environmental conditions, and other relevant inputs. From there, the pipeline focuses on cleaning, synchronizing, and significantly reducing this high-volume data, transforming it into structured, model-ready inputs. This ensures our AI models are working with the right data at the right scale, which is portable rather than being overwhelmed by raw signals. This is our onboard ATMU. It is mounted on an in-service rolling stock. Because it operates during live operations, inspections can happen without disrupting train service. The unit captures track geometry and subsurface conditions under real loaded operating conditions, and it performs onboard pre-processing to reduce noise and filter out low-value data before it enters the pipeline. This keeps downstream analysis focused and scalable. One of our key advantages is that our ATMU is an all-in-one sensing unit. We combine geometry, vision, LiDAR, GPS, and ground-penetrating radar on a single platform. and it allows us to capture a consistent synchronized view of infrastructure in one pass. Importantly, the GPR allows us to see below the surface, not just the track condition, but what's happening in the subgrade as well. This is especially critical in regions with permafrost, where freeze-thaw cycles can weaken the ground long before surface defects appear. By understanding both surface and subsurface behavior together, we can move from reactive fixes to earlier, more predictive maintenance decisions. So this is an example of an image which is captured by one of the cameras on our ATMU. Our LiDAR sensors can then create a highly accurate digital twin of the infrastructure. The scan captures the track conditions and the surrounding environment, such as vegetation identification and growth. Our hardware unit has already been deployed by railway companies such as Hudson Bay Railways in Canada, and the video in the next slide shows one of the earlier field testings with them when we deployed our ATMU unit onto their trains. So the video might be a little bit choppy, but you can see that our unit is installed on an onboard in-service locomotive. Yeah. And alongside the ATMU, we also integrate satellite-derived analysis to add more broader environmental context. This includes insights such as ground deformation and terrain behavior, and that helps us to understand how surrounding conditions influence the infrastructure performance. We also incorporate environmental and weather data to complete the picture. Together, these layers allow us to validate and strengthen our interpretations. For example, subsurface changes that are detected by our GPR can be cross-checked against satellite-derived ground deformation trends and local climate conditions, giving us higher confidence in what we're seeing rather than relying on a single signal. This multi-layer context helps us to interpret risks earlier and more accurately. One outcome of this approach is the ability to predict track temperature based on environmental conditions, which is another use case I'll explain shortly. This slide shows why structured data pipelines matter. By aligning LiDAR, camera, and sensor data into a common synchronized format, we turn raw signals into consistent inputs for our algorithms. This allows us to perform track geometry and condition analysis alongside defect detection, using the same underlying data foundation. Only with structured data pipelines can models be trained reliably across modalities, improving both predictive performance and confidence in the results. Once the data is structured, we move into analytics through machine vision models. These models operate both at the image and pixel level, allowing us to detect and classify defects with higher precision rather than relying on simple thresholds. Importantly, we explicitly manage uncertainty, distinguishing true defects from false positives. This helps to ensure that whatever gets flagged for review is meaningful and actionable and not just visually different. Our models are designed to be real-aware and work seamlessly across our sensors. The same defect can be identified in camera imagery and confirmed through LiDAR geometry, improving confidence in the result. By fusing multiple sensing modalities within a common framework, we move beyond single sensor detection towards a more reliable inference. This forms the basis for decision intelligence, where outputs support prioritization and planning, not just detection. All of the insights generated across sensing, data pipelines, and analytics come together in our Apollo dashboard, which serves as the primary interface for our customers. We've intentionally designed the interface to feel similar to real operators with a QGIS-style experience. This makes it easier to navigate, interpret, and act on insights without changing existing workflows. The same dashboard supports multiple users and multiple applications, from defect analysis to maintenance planning, all in one place. By translating model outputs into clear visualizations and prioritized actions, we make decision-making faster, more consistent, and easier to scale across the network. This brings everything together into our end-to-end Apollo solution, from data collection to data management and processing, and lastly, reporting and visualization in a single integrated framework. This framework forms the foundation of our platform, and we adapt the same underlying technology across different railway and infrastructure use cases, depending on the operational needs of our customers. So for example, for our railway operators, one application of this framework is culvert monitoring. Manual culvert inspections are slow, inconsistent, and often infrequent. We use teleoperated drone-based inspections with real-time data upload and analysis, making inspections highly effective even in remote regions. While AI detects issues like blockage, corrosion, or erosion, and surface risk directly in a centralized dashboard for proactive maintenance. And the dashboard you see here is the same dashboard I showed earlier. Another example would be predicting track temperature. Today, train speeds are often set reactively based on current conditions. Here, the black line shows the actual track temperature, while the red line shows our prediction, allowing operators to anticipate heat-related risks earlier and manage speeds more efficiently across the day. We also provide a rail-specific weather forecasting system. Instead of relying on generic weather reports, operators get location-specific visibility along rail corridors with short-term forecasts and alerts for upcoming risk conditions, supporting faster and more informed operational decisions. So as you could see, the culvert monitoring, weather forecasting, and predicting track temperature can all be seen on the same dashboard, and we customize all these solutions for our railway customers. Another application apart from railway monitoring would be applying this same sensing and AI framework to road monitoring. So we've already retrofitted similar sensor suites onto service vehicles, and we've been able to detect and monitor road conditions, detect vegetation obstructing signages, and identify both surface and subsurface risks, all using the same data pipeline and analytics stack. A further extension of road monitoring would be winter and ice road monitoring, which is very relevant in Canada. So for winter and ice roads, especially in the Arctic and northern communities as well, safety and accessibility depends on constantly changing ice and ground conditions. We combined field sensors with satellite and environmental data to assess ice thickness, monitor freeze-thaw behavior, and identify emerging risk zones in near real time. These insights allow operators to make safer routing and access decisions earlier with far less reliance on manual checks, helping to keep the critical supply routes open while reducing the risk at the same time. Again, the same framework also extends to other critical infrastructure. For example, our technology can be integrated onto existing inspection platforms such as PIGS, pipeline inspection gauges, to support positioning, signal communication, and defect analysis in pipelines. The key point here is that whether it's rail, roads, pipelines, or tunnels, the underlying framework remains the same, only the sensors and the context changes. At a high level, our value proposition is about making infrastructure monitoring more scalable, more predictive, and more actionable. Our solutions are modular and cost-effective, so they can be deployed incrementally. By combining sensing, data pipelines, and AI, we turn raw data into predictive insights that operators can actually act on, helping to prevent failures and extend asset lifespan rather than reacting after the issues occur. We work closely with rail operators, infrastructure owners, and industrial partners to validate and deploy these solutions in real operating environments. This includes active collaborations across railways, infrastructure monitoring, and energy systems, as well as ongoing discussions internationally as well. These partnerships will ensure our technology is grounded in real operational needs and continues to scale across different geographies and asset types. Yep, and with that, I'm done with the presentation. Thank you, and we open the floor to questions.
Oh, thank you very much, Pragya, for this interesting presentation. I now share my screen again, coming to the questions. And there are some questions from the chat and also two pre-prepared. The first one is, how does Apollo's AI layer generalize across different infrastructure applications rather than solving a single inspection problem?
Yeah, so thank you for the question. What happens is that our sensor suite, we don't act immediately onto the raw data itself. So everything will first go through the same structured data pipeline and the context layer. And this actually standardizes how the asset conditions, environment, and operational constraints are represented. So once the different infrastructure types are expressed in the same structure, the same AI and decision logic can be reused, just that the data would be different, but everything else will be the same. So that's how we are able to generalize it.
Yeah, coming to the second question, which is, what role do partnerships with operators and technology integrators play in scaling these solutions internationally?
Yeah, so I think this would be true for any company that is doing this as well, right? So working with different partners is very, very critical to us because it allows us to do to have more contracts, to do more pilot testing, and it also gives our systems the opportunity to actually work with local standards, their operating rules and constraints, while we keep the core technology consistent. So it gives us more experience in how we can actually customize the solution and validate our technology in more real world conditions, because every partnership, every condition could be different. So yeah, this would definitely help us to accelerate deployment and scale internationally without redesigning the solution from scratch. Yeah.
Yeah, thank you. Third question, which is the maximum speed of the train carrying the ATMU?
Yeah, maybe I would like to invite Oliver to answer this question.
Yeah, good morning. So right now our design speed is 100 to 120 kilometer per hour. So that's basically, for the current purpose, the purpose of VTMU, and also the sensor we use, that will generate the good enough resolution to detect the defects and also get a good information for the predictive maintenance.
All right, thank you, Oliver. Good morning, Oliver.
Good
Also
morning.
from my side, the next question is also related to ATMU. Within the ATMU, how do you transfer data from the sensors, LiDAR, camera, etc., to the processing unit? Do you use fiber optic?
So it really depends on the infrastructure, the partner, the customer has. So right now we have a few solutions. One solution, we just like manually transfer data, like we swap the hard drive. And second, we use, if the local, there's some infrastructure allowed, we use a fiber optic. And also we are collaborating with a Montreal company. They have like optical, they have the remote fiber technology. So that can allow the, without physical connection, we can transfer data from the unit to the server.
Yeah, thank you. There is a last question at the moment, but you are we have plenty of time. Please continue to put your questions into the chat or raise your hand. The last question so far is where the weather data come from, which satellite service?
Yeah, the data, the weather data we purchase the weather data from the supplier. So there are many suppliers in the world, and they provide pretty much similar the data content. And the satellite service we use right now we use a Sentinel-1 and also a radar site satellite service.
All right.
Yeah.
Yeah.
But we are open to, to other the satellite service as well. So pretty common, common same algorithm, but just a little bit customization.
Yeah. Thank you so far. And there is another question from the chat. I'm late to copy it into the slide, so I read it directly from the chat. Do you also develop and build the hardware ATMU or just the software? Is the hardware already in regular use or is it still a prototype?
So we developed and build the hardware, and of course, software the algorithm. So we build a full data, full data data layer from the data collecting, the hardware sensing unit. We developed the mechanism to transfer the data, and we pre-processing the data, and on the cloud we also process the data and give the analysis, and then get everything we analyzed for visualization and reporting on the dashboard. So we basically the full data pipeline from collecting hardware to the final report. So we have a hardware is regular used in on we have the unit install the locomotive in January 2024. It's been there almost like 2 years on the locomotive. So it's continuously collect the data and give the data. So we do the analysis. But at the same time, we always improve the design. So get better data, get better processed.
Mm-hmm. So thank you for this huge explanation. Are there other questions so far? Maybe some of you raise your hand and say, "Oh, I have a question." And for sure, we have some minutes left. As it is not the case at the moment, you have some minutes time for your questions. And there was another question referring to presentation. Oh, there is one question already. And data of the ATMU are locally recorded or transmitted in real time to a control room. That is the next question.
So because of the data, is too big, so we cannot transmit the data real time to control room. Like we cannot transfer all the data to the control room. But if critical, we can do the critical information transferred in real time.
Okay, thank you.
So, I think there's one question. Possibility for sensor fusion and cooperation from Peter.
Yeah, might be that is the question I have foreseen also for Julia. Julia
Yes, yes,
answered already in the chat, but if you have also contribution to that question, please proceed.
yes. Yeah, of course. Yeah, we have a experience. We are in Canada, but we have a lots of connection. Conversation with European uh, railway industry, and currently, yeah, we are uh, partnering with ASV, so a Spanish infrastructure company. And yeah, we work together. I think really, the collaborating, the cooperation between two companies really make a difference to the project development. So we, we understand the different regulation requirement, and also geographic environment are also very different. So that will help us to customize the algorithm, and also they have they have some development, and we can exchange information and learn from each other.
Mhm.
So we are always looking for the potential of cooperation.
Yeah. Any contribution from your side, Julia, on this question?
Yes, also from my side, we would be happy to work together and to have a look at sensor fusion options, because it just makes sense to fuse the data and to get more information out of it. And also I have a remark about the question Juan Garcia asked before with the damage in the rails. Maybe it's not possible with the point cloud data. It depends on the resolution. We already said this. But at SIGNON, we are also working with other sensor data, so with video data, with sensors that are looking downwards onto the track. And I guess there we can also make a cooperation and dive deeper into this question, how we can detect such damages. So I will reach out. Yeah, thank you so much for your questions and contributions.
So I can detect the complementarities of both presentation. I can detect the willingness of cooperation between the presenters and also with the presenters with the audience, and that is exactly the goal we want to reach with our ERCI webinar series. And today we had the first time a presentation from a Canadian company, and it came from our business mission we did last year in September to Montreal and Toronto, and we learned a lot about the railway ecosystem in Canada, in both regions, in Ontario as well as in Quebec. And thank you very much for your interesting presentations. Yes, the audience is invited to quote both presentations as well, and also quote the organization of the webinar. And what is the most important to give us some ideas on future topics for future webinars. Or you say, oh, I have also an innovative solution and I want also to present it. You are invited to do so. Please let us know in our short feedback questionnaire. There is much opportunity to raise in a small text and you can text your suggestions and your proposals as well. The link to the questionnaire you will find shortly in the chat. And then I will proceed. The webinar will be recorded and it will be visible in a few days at the YouTube platform of our former STARS project, where all the other webinars from the early past will be visible as well. So the link to our questionnaire is just in the chat. So I will announce the next two webinars in 3 weeks. Also Wednesday, also 10 o'clock Central European Time, we will deal with the topic Smart Rail Engineering, Material Inspection and Interior Solutions. The registration link is just in the chat. You might register already. Then the next one is the special one. It is a combination of ERCI webinar and webinar of the European American Chamber of Commerce in Florida, where ERCI is a member of. It is on transatlantic perspective on securing critical raw materials and components in a fragmented world. And it's special because it's not on Wednesday, it's on a Thursday, 19th of February, and it's not in the morning in Europe, it's in the afternoon in Europe, but in the morning in America. It's 16 o'clock Central European Time and 10 o'clock Eastern Time. And this webinar will have also connection with a project called LiDAR 2030. My colleague Guido will give you some explanation on this project later on. So, events. Yeah, our yearly event I already mentioned are the ERCI Innovation Award. This is the picture of the last winning companies, Top Rail, Composite Braiding, and NAT. And now we are going to start the new contest for 2026. First step is the application on national regional level at your ERCI member cluster. Please contact your ERCI member cluster and get to know how to deal with and when to give our ERC member clusters an idea whom to nominate for the European contest, which is the second stage of our contest. The deadline will be around mid of June, I guess. It's not finally defined so far, but within the next few days, weeks, we will have the exact data also for that. That means we have 18 ERCI member clusters. Each of them is able to nominate up to 3 applications. So in the end, we have maximum 54 applications. Then we will have an international jury, which takes the summer break more or less to evaluate all the applications. And then we have 3 prizes: the best small and medium-sized enterprise, the best large enterprise, and coup de coeur special jury prize. The awarding ceremony will take place during the InnoTrans this year between the 22nd and the 25th of September. You can get some more information on that by following the link here at the end of the slide, and it's already in the chat. So, Canada event. This year, the TRAX Rail Day will take place on 17th and 18th of June in Toronto. And we have 2 ERCI opportunities exhibiting at the ERCI joint booth. There is still 1 place free. And you could also be a delegate of a business mission connected or visiting the Rail Info Day and have some interesting sessions. It's still possible to take the last opportunity to participate. If you're interested, please get in contact to Anne Dombrova from RailS. The mail you find here in the slide and also in the chat. And more details you'll find on our ERCI webpage. So, railway interchange, we stay in America 2 weeks before the TRAX Info Rail Day. The railway interchange takes place in Omaha, in Nebraska, in the United States. Same opportunity exhibiting at the ERCI joint booth and being part of the business mission. Expressions of interests are possible until the end of the month. Details and registration you will find by following this link, which is already in the chat. So, funding opportunities. I have prepared, or we have prepared 2 slides. There is a new funding opportunity for the Europe's Rail Joint Undertaking, a new call for proposals two topics on innovation for regional rail services and new guided transport systems, and safety and certification guidelines and demonstration of safety components for Hyperloop. Both are research and innovation actions, means up to 100% funding for each participant. European projects in general, at least 3 participants from at least 3 different eligible countries. That means also Canada is eligible. There will be an info day online on the 9th of February. The call details you find in the annual work program of Europe's Rail Joint Undertaking, and the deadline for submitting call proposals are the 7th of May. 700 Brussels time. That is the official saying by the European Commission. So, second opportunity for sure is Horizon Europe. There is a plenty number of call topics open, and we restricted in this slide only the reference to certain work programs of the Horizon Europe program, which might be interesting also to the railway sector. That means, for instance, on civil security for society, on climate, energy and mobility, on food, bioeconomy, natural resources, agriculture and environment. Then there is a possibility to contribute in missions and the new European Bauhaus facility that are 100 of pages to read if you follow all the links. And there will be some Horizon Europe info days available within the next days, and also in February and March on very different topics for calls within the Horizon Europe Research and Development Framework Program of the European Union. Then projects, and then I give the floor to my colleague Guido from DTEC Fair, and he is also the operating director of the Europe's Rail, of the European Railway Clusters Initiative. Guido, it's your floor.
Thank you very much, Lutz. Yes, I will try to be short and giving you some ideas and information concerning two European projects. One is called LiDAR 2030, which aim is to learn for European autonomy to deliver Europe's rail projects in 2030. What we have seen is that we need to have some measure in order to strengthening the resilience of European supply chain of raw material and electronic devices for the railway sector. Otherwise, it will not be possible or more difficult to deliver the research and development and innovation project issued by Europe's Rail when it will be time for manufacture the product, subsystem and system defined under the research projects. So you find this project and the links and the project news in the bottom of the slide. The duration of this project is up to end of March, so we are in the final phase, while on the left-hand side you see the 4 partners who are contributing to this project: ERCI, us, and GKZ, which is the mining cluster based in Saxony, Railenium, the technological center of railway based in Valenciennes, France, and Technopark Istanbul in Turkey. Next slide, please. So why we are presenting this is because we are in the last part of this project, and we have now defined a public consultation where all of you are invited also to contribute. I will just read a little bit quickly amongst this slide that the first hyperlink is for defining the project goals, but it's mainly answering to the key question: will there be enough raw material and components to bring to the market in 2030 all the railway innovation of Europe's rail is delivering? Now, what we have done at the project level, we have defined a document, which is this LiDAR 2030 Intelligence Analysis and Recommendation to Deliver Europe's Rail 2030. Okay, it's composed by 3 parts. So the first one is a state of the art. The second one is a snapshot of how rail value chain has been already impacted by supply disruption. The list is impressive. So based also on this experience, there is a set in part 3, a set of recommendations for both the rail and raw material industry, in order to try to limit the disruption and be able to deliver what we have to deliver in the next years. So the kind request to all of you is to contribute to the document by validating or integrating or confuting the practices and recommendations which are listed in part number 3. And to do this, there is the last line, the hyperlink, where the survey is available until the end of February, and to ask you also to upload your position document on the consultation platform. So there is a list of problems, of issues, of recommendation from an industrial or a policy point of view. Everybody is impacted in a way, big or small, but what is interesting is also to hear your voice, to hear your position. So I ask again to kindly answer to this survey. You have time, certainly. We will promote it on all our channel, certainly, but this is an opportunity that I take during this webinar. Thank you very much in advance. Next slide is the project idealist, which is working on free industrial ecosystem and tackling supply chain disruption. Again, you will say yes, and boosting advanced technologies uptake, especially for small and medium enterprises. The consortium is composed by 14 partners. DTECFER, for which I'm working, is one of the partners, and we are in charge of several activities that we will see in the next slide. We still have time until November 26, but the next activity is the Hack and Match event number 4, which is this time based on focus on advanced technologies for manufacturing industries, and the subtopic are additive manufacturing and hybrid processes, advanced robotics, and autonomous systems. So what we are doing, we are collecting up to the 13th of February challenges, so problem, questions, possibilities of improving that companies can put in evidence. Then we will have a call for solution. Other European companies will try to bring answers to the challenges on this topic. And then there will be the 1st and 2nd of April, today I can match the real one, where challengers and solution providers will be together in order to see what they can do. Then there will be an awarding ceremony. Just to anticipate that there is also an Hack and Match number 5, which will be later on all the advanced technologies. The other, yes, thank you, Lutz. Okay. The other activity that we are supporting in this project is called LEX, Learning Expedition. It's, again, a way to through vouchers for SMEs in order to support some of the cost, invite SME to move and to travel and to be together on some topics in some place. The next one and the last Lex number 5 will be in June in Nantes. And it's again based on the topic is additive manufacturing and hybrid processes. So this is what we are proposing you, and we invite you to follow the links for the Idealis project in order to register if you are interested, especially for the SMEs where there is this possibility of receiving a voucher of 500 euros covering part of the travel and accommodation cost. Okay.
So coming to the end of this webinar, I'm repeating to announce the next 2 webinar opportunities on the 11th of February 2025 on Smart Rail Engineering, Material Inspection, Interior Solutions, and the second one on the 19th of February. It's a Thursday, joined with EACC Florida on transatlantic perspective on securing critical raw materials and components in a fragmented world. For both webinars, you can already register. And that is the end of the webinar. You are kindly invited to follow our short questionnaire, and we are keen to learn something more about your suggestions for future topics. So thank you very much, and have a nice day. Thank you to all the presenters and to all of you for this very interesting webinar. All the best to you. Bye-bye.